Okay, so that gives us enough of a picture of the bonding that exists between molecules and metals and nonmetals. And now we need to understand what might exist between molecules, so the intermolecular forces that might exist. So to open with this, we'll consider three types of intermolecular forces. There can be dipole-dipole forces. So a dipole arises when there's a permanent asymmetry to the sharing of electrons in a covalent bond. Okay, so the attraction between the result there is that if there's dipoles on two different molecules, there can be an attraction between those permanent dipoles in those polar molecules. The attractive forces here cause the molecules to come together and often condense to form solids or liquids. So take the polar covalent compound HCl and consider the electronegativities that you might guess for hydrogen and chlorine owing to their position in the periodic table. Recall that chlorine is a neighbor to fluorine down the column, so it is next to the most electronegative element in the periodic table. And see if you can settle on what the dipole might be for that HCl molecule. And then consider putting three HCl molecules next to each other to align dipoles in a fashion that brings together opposite partial charges of that dipole. You can take a minute to sketch your depiction of these three HCl molecules and then resume the video when you're ready. Okay, so hopefully you were able to at least draw three HCl molecules in some sort of an arrangement. There might be many ways to draw all three of them together, but what's important is to denote the molecule's permanent dipole in some fashion. So here we have a partial charge of plus at the less electronegative hydrogen end of the molecule, and a partial charge delta minus at the more electronegative element of chlorine in the HCl molecule. So the dipole here points towards the chlorine, and we often represent that dipole with an arrow with a crosshead at the more delta plus end of the dipole. You can use an arrow like that, or you can use the delta plus delta minus part of the HCl, the delta plus delta minus notation for that. And so if we consider the chlorine as being more negative in partial charge due to its electronegativity value, its ability to attract electrons away from the hydrogen towards the chlorine to give us more electron density over at the chlorine half, then it makes sense to try to position the next delta plus on the neighboring molecule near that delta minus. So here's an intermolecular force between two molecules, and that is to say that the one dipole is attracted to the opposite site on the neighboring molecule's dipole. So we have the arrowhead of the one dipole trying to get close to the crosshead of the other dipole. Okay, so if we were kind of lining them up head to tail, that would show that pattern and those intermolecular forces. In the other dimension, we might consider kind of flipping the HCl molecule so that the delta plus would be, again, close to the delta minus of the neighboring molecule, and that the corresponding delta minus of that third HCl molecule is, of course, aligned with the delta plus on that neighboring HCl molecule. So again, these are permanent dipoles that we've used to describe forces between these molecules. So these are dipole-dipole interactions, and they result in partial charges on one molecule attracting the partial negative charge on the other molecule. Okay, the next are induced dipole forces, or sometimes termed London dispersion forces, and these are weaker in generally because they do not rely on permanent dipoles. They rely on more random fluctuations in the electron cloud to give us temporary partial charges. Okay, so we'll see this, that it is always present in all types of atoms and molecules. So this is an intermolecular force that exists across all types of molecules, but is very weak. And again, it's based on random fluctuations in the electron cloud, or that electron orbital that is the result of sharing of electrons, and it results in temporary dipoles. So in the animation below, you can see momentarily there's no asymmetry to the shared electrons shown in green, but in a brief moment, one might have a fluctuation to position more electron density to one side of the molecule, and then that is going to instantaneously attract the nucleus of a neighboring molecule and push away electrons to the other side of the molecule to induce a temporary dipole in that molecule. Okay, so the snapshot when there's an intermolecular force due to some partial charges looks similar to dipole-dipole, but again, this is a random fluctuation and it only occurs briefly and gives us a momentary condition for establishing some opposite charges attracting one another. Okay, so we mentioned that this type of force is very weak. It occurs between all atoms and molecules, and it's temporary dipoles that are caused by a distortion of that electron cloud. And so you can see another picture here. Before distortion, the charges on a rainbow chart here are largely similar and zero, so evenly colored across the the independent atoms. So these could be, in fact, even inert atoms like the argon atom, which you otherwise wouldn't expect to have very good bonding between each other. But momentarily, there can be a fluctuation in the electron clouds on the argon atom, and that can position more electron density towards it. So you can see here, on this side, we can have a little bit more yellow, so that might mean a little bit more delta minus to that side, and that would impact the electron cloud at a neighboring argon atom, and the delta plus would polarize the electron cloud distribution at that neighboring argon. And in that brief moment, we would have some attractive force. Okay, so this London dispersion attraction, or as your textbook refers to it, induced dipole, will increase with some conditions on the molecule. One, the size. So if the contact area of the atom or molecule can be large, then we can have more electron cloud distribution to work with and potentially distort. Also, the polarizability, so how loosely held the electrons are, or the sloshiness, if you want to consider liquid in your picture of the electron cloud, how low viscosity those electrons are about the nucleus of the atom or molecule. So when electron clouds are held really tight, really close to the nucleus, we are not sloshy, and the electron cloud would be difficult to distort and establish the London dispersion or the induced dipole bonding. Okay, so here's a question to see if we've got it. So take a minute to consider this question and pause the video as noted. So what we want to ask is how do induced dipoles or London dispersion forces work? Well, they're caused by either A, B, C, or D, partial charges from polar molecules interacting with each other, partial charges caused by temporary shifts in the electrons, full charges from ions interacting with one another, or full charges from ions interacting with partial charges on a molecule. Take a minute to take your answer and then resume the video when you've got your answer. Okay, so hopefully you saw that we were emphasizing the temporary shift in electrons to give us some partial charges that would establish a brief moment of dipole interactions. So it's this temporary shifts that's the key there. Okay, here's another one to see if you got it. Induced dipole, or these London dispersion forces, they are only found between nonpolar molecules. They are only found between polar molecules, or they're only found between ions, or they're between all molecules and atoms. Again, take a minute to answer and resume the video when you're ready. Okay, we said it a few times, but yeah, they're found on all molecules and atoms, and of course, depending on the size of the electron cloud and how tightly held it is, establishes how strong the London dispersion force can be, but we can expect them on all molecules and atoms, so the answer D is correct. Okay, third type here for an intermolecular force is, of course, the hydrogen bond. So this is a special dipole-dipole, permanent dipole force, and it's quite strong. And here we'll define it as an attractive force that happens when a hydrogen atom is bonded to an electronegative atom. Okay, so we have to satisfy that condition. We need to have a hydrogen bonded to an oxygen, a hydrogen bonded to a nitrogen, or a hydrogen bonded to a fluorine. And we're going to attract that hydrogen atom is going to be attracted to the lone pair electrons on a small electronegative atom. So that is, there's going to be lone pairs of electrons not shared in bonds, and that these lone pairs are going to interact with hydrogens on a neighboring molecule to give us the hydrogen bond. So we need to, one, have a hydrogen on an F, O, or N site in a molecule. So we need to have a hydrogen on a FON site, so hydrogen bonds are FON. And we also need to look for a FON site on a neighboring molecule that has a lone pair available for the hydrogen bond. Okay, so here's a couple of examples. Here you see the HF molecule. Here's a hydrogen on a FON element, and we're going to look for an FON element on a neighboring molecule, and we're going to see a hydrogen bond between the two. So there's a hydrogen bond. Likewise, down here in water, the famous water molecule, of course, has a hydrogen bond. Same thing there, hydrogen on an oxygen of one molecule, and lone pair oxygen on a neighboring molecule to give us the hydrogen bond. And likewise down here in ammonia. Okay, you might be asking, why is it so special? Well, based on electronegativity differences, we know that the hydrogen is low in electronegativity compared to the FO or N element, so that's always going to give us a delta plus on the hydrogen site. And an FO or N element is, of course, always delta minus because it's very high in electronegativity, so this sets up a very special dipole-dipole interaction that is labeled the hydrogen bond. So that is the sort of way to explain the FON kind of requirements there. We'll see that these are often very short bonds, so they're on the order of the length scale of typical covalent bonds, just a bit longer than a covalent bond. Covalent bonds are on the order of about 0.2 nanometers, and here we have just about 50% longer, and therefore just a bit weaker than covalent bonds. Typically around, hydrogen bonds are typically around 40 to 60 kilojoules per mole, whereas we saw covalent bonds were on the order of hundreds of kilojoules per mole. Okay, some other interactions that we'll just put on your radar. Here's the water molecule again. We know that it has a permanent dipole, and that permanent dipole can induce a dipole in a neighboring molecule. Okay, so this is different than the London dispersion forces because we have a permanent dipole on one molecule, and we can polarize the electron cloud on a neighboring molecule. So we've induced a dipole in this O2 molecule, and this is in fact how oxygen dissolves in water. It relies on an interaction between water and the O2 molecule by way of this dipole-dipole induction. So dipole-induced attraction. Dipole-induced dipole. Be careful with the terminology there relative to your textbook. Previously we had dipole-induced only. Now we have dipole-induced dipole, given that we have a permanent dipole in one molecule. Okay, so let's see if we can put it all together with another example. So here's a multiple choice type question. We've got 5 substances to consider, and we want to list the intermolecular forces that might be expected. So we've got a symmetric trigonal planar molecule in BF3. And so we have fluorine very electronegative at each of the corners of this trigonal plane with a boron at the center. And we want to understand if we have either London dispersion forces, dipole-dipole, or hydrogen bonds present. In the next compound, we want to consider isopropyl alcohol. So this is rubbing alcohol. And we want to know if there's the same type of forces present. So we're going to kind of apply check marks to the spaces in this box. And then we'll do the same thing with hydrogen iodide, HI, and then even krypton, a noble gas, and then our polyethylene. So take a minute to complete the table. Look to apply entries in this table here. And we'll resume the video when you're ready. Okay, so hopefully you would have come up with answers like this, where in the symmetric BF3 molecule, that we would not have a permanent dipole because all dipoles are symmetric and evenly distributed about the corners of this trigonal plane. So dipoles cancel in this case, and so there's no dipole-dipole interactions. Okay, so this was the example like we opened with HCl. We would not see similar dipole-dipole interactions like we saw with HCl. We know that London dispersion forces exist in all molecules and atoms, so we know that that check mark should go there, and therefore we can apply it to each compound in question down the series. A bit easy there. And then in the hydrogen bond circumstance, considering compound A again, well, we need one of those, a hydrogen bonded to an FON element, and I don't see a hydrogen on the BF3 molecule, so we're not going to have anything there. Compound B, isopropyl alcohol, what we discussed there, we're going to have the London dispersion forces, or the dipole induced, as we said in your textbook. We can ask, is there a permanent dipole? And if so, we would expect dipole-dipole interactions. So of course the oxygen, being very electronegative, is going to draw electrons towards it. So we're definitely going to have dipole-dipole interactions, similar to what we had in HCl. Further, because isopropyl alcohol has an OH group, as indicated right here, that OH group has a hydrogen bonded to one of the FON elements, and so we're going to be able to have that hydrogen bonded to another oxygen at another isopropyl alcohol molecule to give us the hydrogen bond. So we're going to see that there as well. In hydrogen iodide, largely similar to the previous with one exception, so we're going to, of course, see the London dispersion forces. We again have a large difference in electronegativity, so we are going to see a dipole in the HI molecule, again pointing towards the halogen, and therefore dipole-dipole interactions. But because we've moved away from an FON element here, we have a hydrogen on a non-FON element, so we do not have a hydrogen bond possible. D, krypton, an inert gas. The krypton seldom reacts with anything. We know that it can have London dispersion forces if we can distort that electron cloud about the single atom site of krypton. So there will be some London dispersion forces there. Can't have any dipole-dipole or hydrogen bond circumstances. And then now in the polyethylene that we considered earlier, we're going to see London dispersion forces throughout, again, because they exist in all molecules. We're not going to see dipole-dipole because the electronegativity difference between carbon and hydrogen is largely quite small. So the electronegativity value of carbon is about 2.5 on that scale, and that of hydrogen is 2.1. So this difference is negligible. So for us, and we're not going to consider that strong enough to give a permanent dipole, and therefore we're not going to list a dipole-dipole. So typically, the delta En to allow us to consider, so the change in or the difference in electronegativity values that will allow us to consider a permanent dipole, we want to consider this value being greater than about 0.9. Okay, so in this case here we only have about 0.4. Okay, so we've largely considered all types of materials at this point. We've looked at ionic bonding, covalent bonding, seen some secondary bonding, so that is between molecules, so we now have some terminology there. We've looked at metallic bonding now. We've looked at how even noble gases like argon can have London dispersion or induced dipole interactions to give us a little bit of weak bonding between argon atoms. And then when we have permanent dipoles, we can have strong secondary bonding. And of course, in this case, the hydrogen bond is going to be found in the water molecule. Okay, so there's some examples of materials to represent all those bonding types that we've considered. And here's some data for the melt point. And so if we're going to overcome any intermolecular forces to allow molecules or atoms to move past one another, those things that are bonded really strongly together through very strong covalent bonds in 3 dimensions are going to have very high melt points. So look at diamond, bonded by covalent bonds in all 3 directions of the material, very, very high melt point. The ionic bond, again, very strong Coulombic forces between oppositely charged ions, and again, a pretty high melt point as a consequence. And if you want to flow ions past one another to allow the molten NaCl to take the form of the container, you're going to have to heat it to 800 degrees C. Polyethylene, much weaker, given that we have very weak London dispersion or induced dipole type interactions between chains, and they're what we temporarily call a melt point here is only about 120 degrees. You'll see when we cover polymers, we'll have more to say about that true melt condition there. Going over to metals again, you can see these are very high melt point, about 1,000 degrees C here for melting pure copper, and that's a consequence of those strong hundreds of kilojoules per mole type metallic bonds from that sea of electrons throughout the packed centers of copper. Okay, and then when we only have weaker intermolecular forces, we have, like we do in argon, very, very low melt points. So only having London dispersion forces present, we don't need to heat very hot at all to melt. The minute you can allow a hydrogen bond to establish, you can program for a lot higher melt points in the material. Okay, so I think we've largely covered a lot of this. And with that, we kind of see how all these things are connected to explain all matter. And so you generally see most covalent compounds, at the top here. Some covalent compounds have secondary forces that owe to their strength. Ionic bonds, for example, tend to be can have some sharing possible, so some matter exists along the bridge between covalent and ionic, and then we have that last class of compounds, which are the metals established through their metallic bonding. Okay, with that.